Hello, good afternoon everyone. I am Tejas from company in India, Interactive Intelligence, and so this is our first submission to the Zero Cost ASR task. So yeah, I'll just skip this motivation part because we have seen the task recap and also the data description. But yeah, the striking thing which I probably would want to mention is it seems that a lot of data was shared by the participants and we just missed it. But good thing I am feeling is like it did not hamper our results by much. So because we did not use the text data for building the language model. So good thing is like luckily probably it did not hamper the data. So I don't have any diagram. So I have lots of text, but I'll go a bit slow in this. So so we used the Kaldi ASR toolkit for building the system, and these were the steps followed. So first was the audio pre-processing. So it was like just the preliminary manual observation. We saw that there were long silences present in the data, and it has been a general observation that long silences many times like create problems for training the HMMs. So we just truncated the long silences to 0.3 second, and as we will see in the next slide where I have discuss the results, that this was the remarkable step, like it brought down the word error rate of the baseline by huge margin. Then was the data augmentation, audio augmentation part. So there was a paper last year in Interspeech 2015. They just augmented the original like 0.9 speed and 1.1 speed versions of the original data to the original data itself, and it did matter a bit, like it created some diversity in the data so that the system learns some new features, because we can see improvements with that approach in the results. Then earlier, the third point is like we use the pitch information. Normally with English language, whenever we train ASR, we normally don't use pitch. It is somehow has been seen that pitch doesn't help. So the conventional MFCCs we use 13-dimensional. But and I was like conventionally using it without the pitch information. But then when I saw the confusions, it seemed like there are a few words which are getting confused, and it is only the tone, because Vietnamese is a tonal language. It is just the tone probably making the difference. So I thought, like, since we already have a tool in the Kaldi ASR, let us use the pitch information as well. So this was use of pitch information was something motivated by looking at the word confusions. Then the fourth point is, so the provided data was around 12 hours, and after we just truncated the long silences, it came down almost by half, like it came down to 7 hours or so. And it has been our general observation also that DNNs or deep neural networks, whenever we have to use, it works remarkably well as compared to subspace Gaussian mixture models. Like there's a big difference between the DNN and the SGMMs when the amount of data increases, whereas SGMMs is like more popular when we have less data. So SGMMs was also something which came out of a workshop which was held in 2009 for low resource languages. So since it had been our earlier observation, we thought like we'll keep the system simple, and also we did not have enough time like to train and to fine tune the DNN system. So we thought like for the acoustic modeling space, we'll stick to the SGMM system. Just like we use MFCCs without the pitch information, so I was just going with trigram language model, and we just saw like, okay, using 5-gram language model is giving us more improvement. But okay, it is not so surprising, but when I increased 5-gram to 7-gram, the result was not as good as 5-gram, so we stuck to 5-gram. So it is more data specific. Then the sixth step is like kind of unsupervised adaptation. So there was around 332 sentence utterances in the test data, and the training data was 1000 utterances. So and of course the test data did not have any transcription, but if we decode the test data using whatever system we have built from the training data and use those approximate transcriptions, so it also helps. So this is actually the final system. In the next slide, we'll see all the experiments, all the 15 experiments which were done, and the red marks are something which did not work. The orange things are something which did not give much improvement as expected, and the black ones are something which I am discussing right now. And then the 6th point was doing the unsupervised adaptation. The 7th point was after we have done the decoding, so there is a lattices or the n-best list which is generated. So it is like kind of a few hypotheses rather than having just one hypothesis. And then since we had already used n-gram language model, which is 5-gram language model, we thought like, okay, let us use RNN also, let us try using RNN because it's a different language model. And then we rescored the lattices using the RNN language model, and it helped a little bit, not as much as we had expected, probably because I did not use a large amount of text for training the RNN language model. So I'll just quickly go to the next slide. So yeah, so the first row is like basic triphone model which I trained. Then since I observed, okay, there is large amount of silences, let us truncate it. So it brought down by around 10%. Then I also tried truncating silences in the test data, but it increased the word error rate. Probably I suspect the reason could be I did not set a proper threshold for truncating the silences in the test data. I just used the same threshold, but I did not dig in much. Why is it increasing? I think that could be one of the reasons. Then for the 4th point, for the 4th row, we just migrated from triphone acoustic model to subspace Gaussian mixture model. And then we should compare like row 2 versus row 4. It brought around 9% improvement, like going from triphone model to subspace Gaussian mixture model. We got 27.4 minus 18.1 is 9.3. Then we just did a very preliminary experiment with DNN model, and it increased the WER. So we just did not touch the DNN model at all after that. And this was not so great experiment. By default, we are using position dependent phones only. Using independent, it just gave some minor degradation. So we again resorted to using position dependent phones. The unsupervised adaptation is something like which I talked just now, like use the test data also in the training for training. And as we can see, it brought 18.1. So I'm just comparing now with 4th row. All the results I'm comparing with the 4th row. So 18.1 minus 16.1. So using the unsupervised adaptation, we got 2% improvement. Then the 8th row is audio augmentation. So this is where we augmented the original data with 0.9 speed of itself and 1.1 speed of itself. And that gave 18.1 minus 17.0 is equal to 1.1 improvement. Then I got a bit more greedy and thought, okay, let us add more data. So let us add 0.8 speed and 1.2 speed as well. So it is, of course, it is giving improvement, but not as much as what we got with just adding 0.9 and 1.1 speed. Then the 10th row was something like I just mentioned, like it was from the observation, motivated from the observation. The tone, there were confusions like which seemed more with the tone, so we used pitch information. Then this is using 5 gram. So the 18.1 is actually with the trigram. So using 5 gram, it got 18.1 minus 16.1 is equal to 2% improvement. But using 7 gram, we were getting just 1.5 improvement, which is not 2%, which is lesser. Then we combined all the systems and then all the above systems, and then we got 13.8 error. And there was some hope that RNN language model would help, but after a lot of fine tuning, it just gave 0.3 improvement. So the reason I am thinking is it needs more data. And then we use the ROVER system, which is like combining all the hypotheses from different systems. It also depends on which systems we are combining. So since I just tried combining all the above systems, it did not give any improvement over the best system. So it was nothing to gain from that. So these are the final results. So yeah, the observation was like we did quite decent on 2 data sets. So basically there were 4 data sets. From ELSA and Rhinospike we did quite well, but relatively poor on data from forvo.com and YouTube. So we need to further investigate what could be the reason. And immediate exploration would be like just explore ways to increase artificially the size of training data, because Baidu is also like improving the systems by adding more and more synthetic data. There was a paper, Deep Speech, so they are doing that. So we could explore, it's a much exploratory domain. And then there's another complementary domain, which is explore ways to robustly train neural network models when you have small data. So one is to increase data to train better neural networks, and one is to look how to improve neural networks using when you have less data. So kind of these are complementary exploratory areas. These are the references. Yeah, thank you.